At the time of recording this video, the last 15 years are the lowest 15 sea ice extents, so how much of the Arctic Ocean is covered in ice, in the entire satellite record, or so we're told. But how do we know that? Do we just have some guy or girl just running around in the Arctic measuring every square meter of ice? No, obviously not. She has a dog sled. Yeah, unfortunately that's not true either. But that's a good thing. I mean, there's over 14 million square kilometers, or 5.4 million miles squared, of water in the Arctic Ocean that, despite global warming and Arctic amplification, is luckily still mostly covered at some point throughout the year by sea ice. That's a little less than the whole of the United States and a half. Which, let's face it, would be way too much work for the poor puppos. So what do? Well, we can't measure from the surface, so we look to the sky. Is it a bird? Is it a plane? Nope, it's a satellite. At a distance of more than 1,000 kilometers, the Nimbus 5, not 2000, was launched on December 11, 1972. Among the many instruments on board Nimbus 5, there was the electrically scanning microwave radiometer, and the data it collected could, very roughly, tell us the minimum sea ice extent in 1972, which was about 7.3 million square kilometers, or 2.8 million miles squared. And that is a little more than the area of Germany times 20. 1972 onwards, and more so from 1978, with the launch of Nimbus 7, not 2001, and the scanning multi-channel microwave radiometer that it carried with it, we have a near complete record of sea ice extent, both maxima and minima till the present day. But how does this all work? To be clear, this is not a video on satellite engineering where we'll be discussing the exact workings of either of the two instruments we mentioned. No, the question here is much simpler, but perhaps not so obvious. How can a satellite tell us how much sea ice there is? So, man-made scientific satellites, devices put into orbit around Earth, or occasionally around other planets, can collect data on Earth or space depending on which direction the instruments are pointed in. Using said satellites, we want to measure sea ice concentration, quite literally an area of sea ice relative to the total at a given point in the ocean. Unfortunately, this cannot just be some giant camera with solar panels sticking out of it. After all, polar regions, what we care about in this case, are in complete darkness a large part of the year, so no visible light is being emitted for our giant camera to capture. Similarly, clouds are a thing, and where there is a cloud, we can't really infer whether there is ice, water, or something else entirely underneath it. You might have noticed I keep repeating visible light, because light that is not visible is the key ingredient here. Specifically, low-frequency light or radiation, which can pass through clouds unlike visible light. We generally only call the radiation in the visible spectrum light, but honestly it's the same type of beast, just with a lower frequency, so less waves pass a single point as the wave propagates forward when compared to visible light. Frequency, denoted by the Greek letter nu, is one of the input parameters in Planck's law, courtesy of Max Planck, one of the greatest physicists of all time that gave us one of the most important formulas. What this essentially tells us is how much energy in a given time for a given surface and a given solid angle, which you can think of as a three-dimensional counterpart to what an angle is, a given body with a given temperature T emits. That T is also in the formula we mentioned earlier, and the B is all of what we just described. And while all of this is quite complicated to remember, what you should know is that everything, and I mean everything, emits some type of radiation. No, not just light sources, and not just living things that generate their own heat, every single thing. But remember, this is not the radiation that helps you see these objects. That's actually visible light reflected off of them. The light radiation they emit is most commonly in the form of low-frequency light. Except objects that are at absolute zero, or 0 Kelvin, or negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. and said objects don't exist. So ice, as cold as it is, emits some type of radiation every second of every day of every year. And that is the radiation that instruments that are meant to assess sea ice concentration capture. Partly because the ice and water have different temperatures, the radiometer on the satellite measures different low-frequency radiation signatures for the two types of surfaces. To be clear, what it measures is not the temperature of ice and water, but rather their brightness temperature, which is the temperature multiplied by the emissivity. And emissivity helps us consider a black body that is radiating the same amount of radiation as the body in question. What's different about a black body? Well, it's black because black is what absorbs all incoming radiation and then re-emits it. That's why it's black. But nothing that's black that we know of is actually a black body. Not even you, Batman. Because a black body absorbs all radiation and emits it all back. That means its emissivity is 1. And most black things we see reflect at least some of it. That's why we can see them, and so their emissivity is less than 1. Now, the last thing to note is that the brightness temperature that the satellite measures is actually not even the brightness temperature of ice or water, but instead, it's what the instrument measures from the top of the atmosphere, because all the gas molecules in the atmosphere can interact with the energy that's being transferred from the Earth's surface to the receiver of the satellite. But even after all that, these brightness temperatures that the satellite retrieves can be categorized such that we can tell with pretty high accuracy where there is ice and where there is water. And that's also how we know that the most recent sea ice minimum in the Arctic was reached on September 16, 2021, with sea ice in the Arctic Ocean covering a total of 4.72 million square kilometers or 1.82 million square miles, which is roughly 13 Germanys, a whole 7 Germanys less than in 1972. Now remember to like and subscribe, and if you want to know why all this ice is melting and what that means for us, check out some of my other videos covering the science behind Arctic amplification, a process by which the Arctic is currently the fastest warming region on our planet.